So we're starting our last week of the semester, and we're going to talk about cold on this first day. So we have a couple of objectives. And so exercise in the cold in some ways is the opposite of what happens in the heat, and that shouldn't be too surprising. Okay, now remember, if it's hot, and let me orient you here. So this is our skin. This is fat, like it says fat, and these are two different blood vessels. So this is one that's above subcutaneous fat, basically a skin blood vessel, and then we've got something that's below. Okay, when it gets hot, the skin blood vessel dilates. Okay, and so a red blood cell can go through it, and it can dissipate heat. Not only, it's not the red blood cell, but the blood itself. Okay, but in the cold, what happens is this blood vessel constricts, and so we send blood to kind of our core. And these blood vessels are below subcutaneous fat, and they're still trying to dissipate heat, but the fat prevents heat from being lost because fat insulates. Okay, and so as a result, when we have low core temperature, we decrease skin blood flow. Okay, and specifically in our skin, or yeah, I said skin blood flow. Okay, and so we have reduced skin blood flow, and so this happens in all peripheral tissues. And what we mean by peripheral tissues is just think like extremities. Okay, so kind of the outside. We're not keeping blood in the core, or we're trying to prevent blood from going to the core. Now, your head doesn't have any what we call vasomotor control. In other words, you don't really have the ability to constrict or dilate those blood vessels. And so your scalp actually doesn't vasoconstrict in the cold. And so you lose heat, a lot of heat through your head, right? So we're getting to that time of year where it's cold outside. My favorite time of year to go running is this, early to mid fall. And, if you watch football, especially if they're playing like, I guess really there's very few, or there's like if they're in Green Bay, guy takes his helmet off, doesn't have a beanie on, and you can just see the steam and stuff coming off his head. He's losing heat. Okay. And that's in part because it's an extremity and we can't reduce blood flow to our scalp. And so what ends up happening is that blood flow is redistributed. Okay. And so this vasoconstriction forces blood into our core or into our central blood volume. Okay. But there are consequences to this, and they're not terrible consequences, but there are still physiological consequences. If I have a lot of blood in my core, or in other words, I'm increasing venous return, I'm going to activate these stretch receptors or these baroreceptors that monitor blood volume. Okay, and so if I've got high venous return or high blood volume in my core, what's going to happen to blood pressure? Well, blood pressure is going to be increased, or at least it's going to be sensed as it's high, and so we're going to want to counteract that increased pressure. And one of the easiest ways to reduce pressure is to pee. And so we increase urine volume, or in other words, we increase urination, and we call this cold-induced diuresis. All right. So when you're in the cold, you're more likely to urinate. And so this is also true, especially if you're like immersed in cold water, because that even forces more blood to your core just with the effect of being in water. So if we come back to the Fick equation, which we've talked about several times throughout the semester, this is it, right? So VO2 max equals cardiac output times the AAVO2 difference. Okay, in other words, heart rate times stroke volume times the difference between arterial oxygen content and venous oxygen content. So how does the cold affect this? Well, first of all, this is key, that in order for VO2 max to be affected, it's the core temperature. We have to change core temperature. Okay, if you remember in class, I told Cohen, hey, if I can guarantee you an A for this class and all the rest of the classes you have to take, you have to run a 5K when it's 30 below or whatever outside, would you do it? And the answer is yes. And he talked about how he would, put on a ton of clothes and try and stay warm. Well, if you're able to stay warm enough, you're not going to impact VO2 max. All right, but if your core temperature starts to drop, then we have some changes. And so your max heart rate is going to be decreased. But this max heart rate isn't associated, or this decrease in max heart rate isn't associated with an increased stroke volume. So your maximal cardiac output's reduced. So in other words, you have your ability to deliver oxygen is diminished. Additionally, hemoglobin binds to oxygen more tightly at low temperatures. Remember, this essentially causes a left shift. Okay, and so when we've got that left shift, it makes it more difficult for oxygen to leave hemoglobin, and so as a result, that also decreases oxygen delivery. So you've got a lower cardiac output, and it's more difficult for oxygen to leave, so ultimately you're delivering less oxygen to the muscles. Okay? It's also possible that you're not delivering as much oxygen to the skeletal muscles because you're trying to keep it in the core. If you think about it, your legs are extremities and it's easy to lose heat. And so if we're trying to limit heat loss, we're going to do some things that are going to reduce blood flow to those extremities. Okay. So how does this affect in the cold? Or how does endurance performance affect it in the cold? Again, if core temperature doesn't decrease, then the limitations don't apply. We need to have a change in core temperature. And so this can actually make doing studies in the cold a little difficult, okay? Because when someone goes out and exercises in the cold, they're going to be bundled up, right? But that'll help reduce heat loss. And so it can be difficult to understand or to create a good study that'll let you know what's going on. Now, when your muscle starts to cool, fatigue actually occurs at a slower rate. So, but if your muscle temperature, remember this is muscle temperature, not core temperature, falls below 27 degrees Celsius, then you have some issues with muscular endurance decreasing, okay? And so this could be, like it says here, your nerve conduction velocity is reduced. Heat speeds up chemical reactions, cold slows it down. We might, as a result, recruit fewer muscle fibers. And so we're not able to do as much. So this is a figure that's recreated from an important study that was done nearly 25 years ago, which is a little nuts, by Galloway and Mon. And what they did is they had subjects complete 4 exercise bouts in different temperatures, and basically they rode at a consistent workload until they couldn't go anymore. Okay, and so all of these lasted for about an hour or an hour and a half. And they were 4 degrees Celsius, which is about 40 degrees, 11 degrees Celsius, which is a little above 50, 21 degrees, which is like 69, 70, and then 31 degrees, which is a little bit warmer than that. So what do you see here as you look at this figure? Well, right here at about 11 degrees Celsius, that appears to be where endurance performance is optimal. Okay, so optimal temperature for aerobic performance seems to be around 11 degrees Celsius, which is about 50 degrees Fahrenheit. Okay, and I don't know if it's because I know this study or it's just how it is. I love running when it's in the 40s and 50s. Like it's delightful. Okay, and so this is kind of where it's cold, so you're not having to dissipate a ton of heat through your skin, but it's not so cold that you're having huge drops, or any drops really, in your core temperature. Okay, now when we're doing endurance performance, and this is the same study, but notice what's going on with VO2. Okay, so this square here corresponds with 31 degrees. Okay, and these right here, these circles correspond with 21, and then this is 11, and then this one is 4 degrees. Now notice that VO2 is higher as it's colder. Now, the theory behind this is that you've got greater muscle tension when it's cold. Okay, and so you have to overcome this tension that's in your muscles. Okay, kind of think of it similar to shivering. All right, and so in order to overcome the tension and to do what you need to do, you need more oxygen, you need to be able to work a little bit harder. And so that could be what's leading to this increase in VO2. All right, and this happens when the thermoreceptors in the skin go, whoa, it's cold outside. Okay, but like I've said a couple times, in order for any of this to really be affected, or for the temperature to affect anything, you have to have a core temperature. So if you wear enough clothes, you're not going to decrease your core temperature. But there are some effects with that. Go back to Cohen, who said, yes, I will run a 5K when it's 30 below, but he's going to wear a whole bunch of stuff, and he's going to look like that kid from Toy Story. Well, this changes things a little bit. And so because the clothing has weight, well, that's going to add to the energy costs needed to do the exercise. He's also going to sweat, and that's going to be absorbed by the clothing. That'll make it a little more difficult. And then you've got to take into account the fact that the clothes that he is wearing, or would be wearing, are going to make it so he can't run as smoothly. In other words, his running economy is going to be diminished, which means it's going to take more energy to actually run a 5K or complete a 5K in 35 below or whatever it is, as opposed to just 30 degrees Celsius. All right. And then the other one is that because we normally wear layers when it's really cold, this actually causes friction. And so that friction causes drag, and to overcome the drag, well, that requires more energy. All right. Now, if it's cold enough, what happens? Well, we start to shiver. And so if you're shivering while you're exercising, well, that increases VO2. Like if you look here, we take an exercise for a given intensity, shivering increases VO2, by 10 or 15%. And so this is because shivering requires oxygen. So VO2 max decreases because cardiac output decreases in the cold due to decreased heart rate. And they think this has something to do with the cold making it more difficult for muscle contraction, which we'll get to on the next slide. But just think of it as the sarcoplasm, the fluid inside the muscle, is more viscous, and so it requires more energy, more effort, more oxygen to overcome that. Now, generally speaking, you start to shiver when you get in somewhere between around 35.5 degrees Celsius, although that is very different for different people. Did a study at University of Oregon where some people didn't even shiver when they got that cold, and we had some people that shivered when they got like 36. And so it just depends. So you have to remember that the nervous system functions different in the cold, okay? Like we said, cold slows things down. It slows chemical reactions down, which means the signals are slowed down, and this causes changes in how muscles are recruited, okay? As a result, you're not able to shorten your muscle as well, which means you're not able to generate as much power. But this comes back to muscle temperature. If we're not affecting muscle temperature, even if it's cold outside, then power production isn't affected either. All right. So I want you to think about this, and then we're going to tie this into swimming here because I think that's a question on your EB. Cold and muscle function, it's kind of a good thing and a bad thing. Okay, so when you start to exercise, you generate heat. That'll help keep your core temperature up. But if you start to get tired, you reduce the intensity at which you're exercising. This leads to a decreased heat production, which will cause your core temperature to decrease, and then this can ultimately lead to fatigue. Okay. Now, if you go back to the different methods of heat exchange, let's say you're swimming. Okay, so you're swimming in the water. You're experiencing a lot of convection. Water has higher convective properties than air, right? And I can't remember if I said this on a previous video, but just to give you an example, if I told you had to put your hand in boiling water, or you had to put your hand inside of an oven that's 400 degrees, which one are you going to do? And the answer is most likely, I know this is a weird question, but you're going to put your hand in the oven, okay? Not touching anything in the oven, just put it in the hot air. Okay, you can put your hand in the hot oven for a little bit, but you won't even be able to handle your hand in the boiling water. Okay, one's 200 degrees, but water, and the other one's 400 degrees, but air. Water has much higher convective properties. And so when we're talking about swimming when it's cold, well, as you swim or just sit in cold water, you're losing lots and lots of heat. And so if you're swimming in cold water, as you fatigue, you're not generating as much heat, and then you're losing even more heat than normal. Okay, and so that's why it can be dangerous, especially dangerous to swim in cold water. All right, 2 more slides. So with resistance exercise, this kind of ties into some of the things that we've been talking about. Nerve conduction velocity decreases, which means you don't recruit as many fibers, which means it's more difficult to reach max force. Your cross bridges aren't able to cycle as fast. Your chemical reactions slow down, so you're not able to break down ATP as quickly. The sarcoplasm has a higher viscosity, higher thickness, so that means more resistance. And so it's just really difficult to generate generate force in your muscles when it's cold. Okay, so to sum up, if the muscle is cold, then you're going to lose the ability to generate power. And this comes of about 4 to 5% per degree Celsius. Okay, remember, but this is the muscle itself. Okay, ultimately because you have slower cross-bridge cycling, you have increased viscosity, and those chemical reactions have slowed down, and those enzymes aren't able to work as efficiently. And so those are some acute responses to the cold.